Hello everyone and welcome back to my channel. Today we are going through all steps involved in the multivariate empirical mode decomposition, in short MEMD. If you haven't watched my previous video on the MEMD, I recommend watching it for some deeper understanding. For example, why we need the key element of the MEMD, which are the signal's projections, or why the MEMD is more suited to multivariate data analysis than the standard univariate EMD. So the main objective of the MEMD is to find and align scales common to two or more one-dimensional signals. These signals can be different quantities that we measured simultaneously, for example different velocity components or temperature and pressure data. By simultaneously decomposing all these signals, scales that are common to two or more signals are found in equal indexed IMFs. This mode alignment property enables us to extract on which time scales and at which time intervals the signals behave similarly. In the following explanation of the algorithm, we will use the tree-variate data G of t. The top image obviously shows the 3D view, and the bottom figures provide top and side view. I have mainly chosen this data for visualization purposes of the algorithm. Since all three components possess the same frequency f1, the resulting modal distributions are not very exciting. If you want to see how the MEMD extracts frequencies common to different signals, please watch my preceding video on the MEMD. The very first step of the MEMD is the definition of direction vectors x. They should be uniformly distributed, and they can easily be defined using a uniformly distributed point set on a hypersphere. You see such a point set on a two-sphere in this figure. Using the Hammersley sequence for defining the point set is always a good idea. However, there's a publication by Hemakom and co-workers who suggest an improved distribution by rearranging the point set in the direction of highest covariance of the data. I personally did not observe significant changes of my results when using the so-called EPID MEMD. But if you like to check it out, I put the reference in the description box below. The authors also provide their MATLAB implementation, so you can easily apply it to your data. Coming back to the point set, independently of the method used to define it, the number of points and thus the number of direction vectors, capital K, is a parameter of choice, and I recommend performing a short parameter study to analyze how the number of projection directions influences your results. The dimension of each direction vector equals the number of variates, capital N, which is 3 for our current signal. That's why the plotted hypersphere here is actually an ordinary sphere that lives in a 3D space. You will soon see why the number of variates and the number of spatial dimensions must match. Since the direction vectors point to each of the points on the unit hypersphere, they could also be defined by the angle theta. That's why we include the angle in the notation. In the following, we will use these four exemplary direction vectors to understand how the signal projections along the directions defined by the direction vectors work. Okay, so in the next step, our signal g of t is projected along these direction vectors, which yields the projections capital P. Mathematically, this projection is just a multiplication of the data with each of the direction vectors. The data G is a matrix with 3 columns, so 1 column for each variate, and the rows represent the time steps going from T1 up to TT. As already mentioned, each direction vector has 3 entries, which enables a meaningful scalar product. Once we have multiplied everything using standard algebra, this scalar product yields a one-dimensional outcome, so a single value for each time step. We see that the projection downgrades our multivariate input data G to a single variate output from which we can easily determine the locations of extrema, which is the primary objective to perform this projection. And we repeat it for all projection directions, So in total, we obtain capital K of these univariate projections. Okay, how does this look like visually for our exemplary data? We are using 4 exemplary direction vectors with k equals 1, 10, 35 and 61. Projecting the data G along these directions yields these univariate projected signals as a function of time. You can see that the blue and the light blue direction vectors point approximately in opposite directions, which yields nearly mirrored projected signals. Of course, in reality, we would do this projection for a lot more projection directions. Next, we can detect the locations of extrema inherent to our projected signals. I have marked them for the 4 exemplary signals in the figure. Then, and this is really important, we do not use the extrema values of the projected signals. Instead, we use the values of the original multivariate data G at the locations of the extrema of the projected signals. For the exemplary projection directions, the extrema locations are found at these positions of the original data. So the projections essentially serve the purpose of telling us where the extrema locations are. By then using the original data at these locations, we can recover our multivariate structure. Then we interpolate the values at the extrema locations independently for each projection direction to obtain multiple envelopes. For each projection direction, we get one envelope by interpolating the values at the minima locations and one envelope via the values at the maxima positions. So in total, the number of envelopes equals 2 times the number of direction vectors. If you are reading the original publication on the MEMD by Rehman and Mandic, which you can find in the description box, you will see that they state that they are only using the maxima to obtain the envelopes. However, their MATLAB implementation uses the minima as well. And since I assume that most of you will simply apply this MATLAB code to your data, I have chosen to explain exactly what the code does, even if it is deviating from the procedure outlined in the publication. To be honest, I have no idea where this deviation comes from, but let's get back to the algorithm. Once we have determined all these envelopes that enclose our original data, we average over all projection directions to obtain a single mean envelope. And this is the reason why the direction vectors need to be uniformly distributed in space. This guarantees that the averaging yields a meaningful mean envelope that best approximates the true mean envelope. Please note that I used 64 projection directions to calculate the mean envelope that is plotted in black here, since 4 directions are just not enough for a meaningful outcome. Although this mean envelope nearly looks like a straight line, keep in mind that it is still a trivariate signal, so it contains 3 values for each time step. Next, we calculate a residual by subtracting the mean envelope from the original data. The residual is plotted in violet and nearly looks like a 2-dimensional structure embedded in 3D space. This is because the mean envelope is approximately a line along the z direction, and subtracting it from the original data sets all z values close to 0. Okay, the last step is the calculation of the stopping criterion. It is somewhat more complicated than in the univariate algorithm, since its direct application to multivariate data is not possible. So we need a whole new page to give it the space it deserves. The stopping criterion actually consists of 2 separate conditions that both need to be true to continue the sifting process. Continuing means that the present residual does not possess the characteristics of an IMF, and further sifting is required to obtain the IMF. The first condition considers the number of extrema. Along all the projection directions that we used, at least one projected signal needs to possess at least 3 extrema. In other words, From all the extrema locations T subscript I that we found for the projections K, any, so at least one, must have more than 2 entries. Otherwise, we could not calculate a meaningful or multiple meaningful envelopes. You might remember this criterion in a similar manner from the univariate EMD, where we stopped the whole decomposition once the residual approached a monotonic function. The other criterion tackles the characteristics of the mean envelope, or more precisely, its relation to the upper and lower envelopes from which it is calculated. It is split into 2 parts, and at least one of these subcriteria needs to be true to keep the sifting going. To understand what these subcriteria are looking at, we first need to understand this expression, which we call lambda. The numerator is the root sum of squares level of the mean envelope. This means that we first square all values of the mean envelope, then we sum over all variates capital N, and lastly we'll take the square root from this sum. Remember that the mean envelope lives in an n-dimensional space, which is 3-dimensional in our example. So the summation over all variates eliminates this dimensionality and yields a single dimension outcome which only depends on time. The main component of the denominator is the square difference between the maximum and minimum envelope. It essentially reflects the squared area that is enclosed by these envelopes. As in the denominator, this quantity is summed over all variates n and the square root is taken. So again, this is a dimensionality reduction. However, we still have one enclosed area for each projection direction. So an additional sum is taken over all projection directions capital K. Since we also divide the result by 2k, we essentially average over all projection directions. In other words, the denominator represents the average region that is enclosed by the upper and lower envelope. Since we sum over the variates and the projection directions, the result has again a single dimension, which is the time axis. So we can easily divide the root sum of squares vector of the mean envelope in the denominator by the projected average root sum of squares level of the envelope's enclosed area in the denominator. Lambda is thus a vector with one entry for each time step. And broadly speaking, it tells us the ratio of the mean envelope to the area enclosed by the upper and lower envelopes in an averaged manner. You might wonder why we need such a complicated expression. Recall that our IMFs are typically zero mean signals, so we want the local mean to approach 0. But we cannot just prescribe that the mean envelope, so essentially the numerator of lambda, should be 0. This criterion brings some complications. For example, we do not want to oversift, which means that we would remove all amplitude variations inherent to the data by excessive sifting. And as a compromise, we lower the ratio of the mean envelope to the enclosing envelopes. And if this ratio is small enough, we are happy. In other words, we are enforcing the enclosing envelopes to rearrange around 0, until their enclosed area is approximately symmetric around 0. Actually, this is the first part of the second criterion. Let's see how this formula expresses what I have just said. Starting at the most inner position, we take all entries of the vector lambda that are greater than a threshold value epsilon 1. These are capital G entries, and they represent time steps at which the local mean envelope has large values compared to the upper and lower envelope's distance. This means that the area enclosed by the envelopes is very unsymmetric around 0, so the mean envelope deviates strongly from 0. Thus, the residual is actually very far from being a solid IMF at these locations. We then average the values at these locations and if this mean value is greater than a second threshold epsilon 2, we proceed the sifting, meaning that we do further iterations until, on average, these remaining G locations possess IMF-like characteristics. To adequately deal with outliers, we have the second part of the criterion, stating that the sifting proceeds if lambda has at least one very high value that is greater than a third threshold, epsilon 3. So, in summary, the sifting continues if the mean envelope, in relation to the region enclosed by the upper and lower envelopes, features particular outliers, or if several locations G possess high values. In addition, at least one projected signal needs to contain at least 3 extrema. Although the MEMD is a data-driven decomposition method, you see that the stopping criterion requires some user input to define the 3 threshold values. For a warm start, the MATLAB code by Rehman and Mandic provides default values for this. But you should definitely play around with these values to see how much impact they have on the outcome and to get kind of an intuitive feeling for their significance. Okay, now that we have covered the last challenging part of the MEMD algorithm, let's briefly recap the iterative nature of the whole sifting procedure. Similar to the univariate EMD, we have an inner loop that iterates until the residual fulfills the characteristics of an IMF. So if the stopping criterion is false, the sifting is repeated with the residual. The notation false is actually in contradiction to the statements I made on the previous slide, where I said that the different conditions need to be true to continue the sifting. But it is easier to express the stopping criterion in this way and then just reverse into its opposite to be in accordance with the notation we used for the univariate algorithm. Okay, so the inner loop skips the very first step of the algorithm, which is the definition of the direction vectors. This is only done once, since the same directions are used for all projections. So in the other case where the stopping criterion is fulfilled, we switch to the outer loop. This loop repeats until all IMFs are extracted. Here the residual is assigned to an IMF and the sifting proceeds with the updated signal G of t, which is just the previous signal G minus the novel IMF. The complete decomposition stops when all projected signals have less than 3 extrema. Well, I hope I could provide you a comprehensive overview about the MEMD algorithm. And if there are still open questions, feel free to ask them in the comments and I will get back to you. And if you have particular suggestions or requests that you would like me to cover in another video, just let me know. Thank you very much for your attention and I will see you in the next video. Bye!